Okay, hi. This was a question that James asked me in class today, and it's a really interesting question. And I finally cracked, I think, why the proof works anyway. So, okay, here's an interesting misconception. You've got a matrix here, and you're going to transform a plane using the matrix, and they want you to find the new equation of the plane under transformation M. Now, this isn't a difficult question. You can certainly just do it in a number of ways, really. A couple of immediate thoughts spring to mind is you could just multiply this matrix by your plane here, written as if it was a vector in parametric form, in terms of the two parameters lambda and mu. So you could multiply by 1 plus 2 lambda plus 3 mu, etc., minus 2 plus lambda minus mu, and 1 plus 3 lambda plus 2 mu. That should give you another 3 by 1, if you see what I mean, because you've got 3 by 3 here. This is actually just a column vector. We do rows and columns, so this is going to be a 3 by 1, and so the resulting vector will be a 3 by 1. I'm not going to actually do the calculations. I do that, 1 times that row, 2 times that row, 1 times that row. I'll write it top there, etc., etc. And that will give you a new plane, which, if you call this this new plane written as a vector, R2, you could easily turn that into Cartesian form, and the question would be done. Another way you could do it as well is you could just write down 3 points on this plane and just transform those points and find the new equation of the plane, because when you've got 3 points, it's dead easy to find the equation of the plane. You can use cross product, or you can use a variety of ways of doing it, really. It's not that difficult, but it's very easy to find three points on this plane as well. You could just say lambda is mu 0, mu is 0, and you get that point. You could say lambda is 1, mu is 0, you get another point. Lambda is 0, mu is 1, you get another fresh point. And then you could transform those 3 points by this matrix using your calculator very quickly, find 3 more points, and you could easily find the equation of that plane. Both ways work, by the way. Both ways work. Now, James said, and I completely agree with him, that is it not possible, though, to find the normal to this plane? Find normal. Apply the matrix to the normal, and that will come up with a new normal, and then take 1 point and apply it to the matrix. You've got a normal, you've got a point, you should be able to write down very quickly the equation of the plane. Now, that way will fail. It's wrong. It doesn't work. It doesn't work like that. The normal is not transformed always in the same way that the points on the plane are. That was really interesting to me, because I completely agree with James and said, no, that seems like a way it should work, but it was clearly failing quite badly, the method. And so why doesn't it work? Why doesn't the normal always work, get transformed in the same way as the points on the plane are? Well, after a lot of help online, I eventually figured out what was going on. Now, to first do this, I want to first prove to you an interesting result. Let's talk about this result, which is, weirdly enough, if you've got a matrix and you times it by, and let's say the matrix is 3 by 3, as we're dealing in the 3 by 3 case. If you've got a matrix and you times it by a vector, and then you find the scalar product of that vector and a new vector, interestingly enough, that is the same as taking the original vector and finding the dot product of that vector with the transpose of A times by the vector V. Yeah, so notice like that U's kind of switched with the A, and the dot's moved over here, and it's become A transpose. Yeah, so let me prove that result. A can be like A, B, C, D, E, F, G, H, I. Oh, this is going to be a bit of a grind, this algebra, but it does work. I checked it works, and we'll let U equal U1, U2, U3, and V equal V1, V2, V3. If we now find the left hand side and the right hand side, it's not difficult to do, it just takes a while. D, E, F, G, H, I, and I'm going to be, I'm getting really slapdash now, and I'm going to be dotting that with V1, V2, we're going to be multiplying that by U. Now, it's easy to get a little bit confused here. We're multiplying it by U, and then we're going to dot it with V. Yeah, V1, V2, V3. Apologies that my handwriting's breaking down. It's just because I know I've got to do a lot of algebra. Okay, so U1, U2, U3, and I'm just going to work out what that is. I'm going to grind through it. So I'm going to have AU1, BU2, CU3 on the first row. Because I'm doing that times that plus that times that plus that times that. I'm then going to subsequently have very similar DU1, EU2, FU3, and then GU1, HU2, plus GU3. And I'm going to be dotting that with V1, V2, V3. Now remember, the dot works different to the multiplied matrix bit because now we're finding a scalar. So the final result is a scalar. It's going to be AU1, V1. Oh. Be a little bit careful when you do this. AU1, V1 plus BU2, V1 plus CU3, V1 plus, because it's an actual scalar, DU1, V1. This is going to be a bit boring for you when you're listening to this. Feel free to fast forward this bit if you like. Plus FU3, V3. Oh, God, I'm doing it wrong, aren't I? DU1, because I'm dotting all of that with V2. So all of this should be being multiplied by V2 now. I apologise. DU1, V2 plus EU2, V2 plus FU3, V2. Do you see what I mean? It works the other way to the matrix. So when you do this, it's very easy to get muddled up with the two different methods of what you're doing here. Dotting is not multiplying. It works very differently, doesn't it? And so we've got, and also that is not a 3 by 3 matrix, so you shouldn't be doing it like that. So yeah, then finally you're going to get GU1, V3 plus HU2, V3 plus GU3, V3. Okay, right, that's the left-hand side. Well, funnily enough, and the right-hand side isn't any quicker, but the right-hand side agrees with the left-hand side after you've done it. Let's just go through it. It is tedious algebra. Once we've got this result, though, we've got a lovely result we can use in quite a short proof, I hope. Okay, A transpose is just A, B, C, because that's the first row, D, E, F, G, H, I. So I've just swapped rows for columns. Typical transpose. But I'm doing that first, sorry, times by V1. Not, I shouldn't write times, that looks like cross, but V1, V2, V3. Okay, so I'll keep the U1, U2, U3 sitting there, and I'll do the multiplication first. And sure enough, I end up with A1, V1 plus DV2 plus GV3, and then BV1 plus EV2 plus HV3, and then finally CV1 plus FV2 plus IV3, and now I'm going to dot that with that. Now remember the timesing goes in that direction this time, so it's A U1 V1, yeah, that's the same as that one, plus D U1 V2, sure enough that's the same as that one, plus GU1 V3, well, that's the same as that one. You know, it all works out beautifully. Plus BU2 V1, feel free to skip, plus EU2 V2 plus HV3 U2. Yeah, and that ends up being the same as that one, and that one. And then lastly, CV1 U3 plus F U3 V2 plus IV U3 V3. And they work out all the same. Look at that, I've written G there when I should have written I. You notice little mistakes in what you've written. Look at that, I've got it there as well. Apologies, I did mean I threw out that, so apologies if I messed that up. But look, it's easy to correct at the end because you can see what you should have. There we go, we've got every single term. The left hand side equals right hand side. So, lovely stuff. So we know that that's true. Now, if you know that that's true, then here is basically what's going on. You can always write the form r dot n equals d in a slightly different format. You'd think of the d as basically a scalar product of two other numbers, because you could also write it as n dotted with like some point on the plane x minus like a particular point on the plane. Let's call it x0. Yeah. Now x can represent a general point and x0 can represent a particular point on a plane, but really this is just the number that you plug into here when you're trying to find d, isn't it? Like you know what I mean, like it could be any point on the plane, any random point on the plane satisfies this equation, so you can plug in any x0 in there, and you know, when you do n dot x0, you then add it over there and it becomes your d, if you see what I mean, because n is representing the normal vector in each case and the x is representing the general point on the plane. So this is, you know, just a slightly different notation from normal. Okay, if we apply this matrix rotation, this matrix transformation, sorry, to a point, we could say that any point on the plane, let's just call it x, is going to go to some other point x dash, and so naturally mx0 is going to go to x0 dash. Yeah. Now we could easily rearrange that to make that x equals m to the minus 1 x dash, pre-multiply by the m, and x0 represents that as well. Okay, so I can plug those in to this equation and just make a substitution here and say, okay, so the inverse of the matrix multiplied by the reflection of the point minus, you know, of the general point, if you like, minus the inverse matrix multiplied by a reflection, you know, a transformation, sorry, I keep calling it a reflection. It's not necessarily a reflection, but the transformation applied to the general point. Okay, so now I've got this, what I can do is I can factorize out the m, if you like, according to that property which we're allowed to do with matrices. It's basically the distributive property over addition. Now I'm going to be left with x dash minus x0 dash here, and here's the clever bit. Here's where we're actually going to use this new rule, which is that au.v equals u.atv. au dotted with v is equal to u dotted with at times by v. So it's a way of moving the transpose in there. Now, because the transpose of a matrix is itself, you know, if you transpose twice, you just get back to where you started because you swap rows for columns, and then you do it again and you're back to where you started. So it's important to note that this formula could also be written like this way around as well, you know, like I like to know it anyway, u dot a v, yeah, just pointing that out. But anyway, because of this rule, we can think, well, if this is the transpose, we can actually just rewrite this now and just say, okay, what this is telling me, let me move it across so it's a bit clearer, right in the middle of the page. So what this is telling me is I can apply this rule. So that's what I'm going to do. I'm going to say, okay, I can pull this m out. If you like, I'm pre-multiplying by the transpose of, no, actually I'm just going to pull it out. So if I've got n dotted with a matrix times by a vector, which is this situation here, then I can instead swap the u in there and take out the matrix and just transpose it. And then, oh sorry, not a dot, and then multiply that by the matrix which was the vector which was in here, yeah? So n is my u, if you like, and x dash minus x0 dash is my v, yeah? So I'm now going to go from this side over to this side, and sure enough then, this needs to be multiplied by n, and then that dotted with x dash minus x0 dash, yeah, equals 0. Now if you just inspect this, you can now see that if you were operating with the same points which have been transformed, which is a general point x and a particular point x0, well, the equation of your new plane is going to be this one sitting right here, yeah? and hence the normal. What's happened to the normal? Well, it's actually been multiplied by the inverse of the transpose. Yeah. Now, when you multiply by this, you change that normal. Like it could be a completely different normal, which indeed it is. Like it's not just m n, which is what you might expect. But this is the this is a transformed equation. You can just see it in front of you because look, we want to know what what normal vector we dot with x dash minus x0 dash under that definition of a plane. We want to know what the normal is, and we can see it right in front of us. So if this dotted with something equals 0, then that must represent the normal. And so yeah, this is the new normal to the plane. Yeah, it's the new normal to the plane. It's weird. It's not something to worry about at all. That's my best description from what I can gather of what is going on. I don't think I've particularly explained it very well. I don't think you've got to worry about it. Well, until you see it next year at university, of course, but then you'll have to worry about it. But just be aware that, like, yeah, the normal isn't necessarily well behaved. Now, I think where the misunderstanding comes from is that in lots and lots of situations, m equals m minus t. When does that happen? Well, when the matrix represents a rotation or a reflection, this is true. Any orthogonal transformation, apparently, this is true. And so, if you've, sorry about my t there as well. So you can see why you might think the normal is going to be well behaved under matrix transformations, because they are well behaved under if the matrix transformation is a rotation or a reflection. And so there you go. And that was thanks to an answer on the Mass Stack Exchange, where you can find some great stuff. You really can, in terms of like when you're confused why a particular assumption isn't working. So that's why when you get something like that, do it the easier way. Don't mess around with the normals. Basically, it's one of those very rare situations where it feels like that should be right. I think it feels like that anyway. But there we go. It's an assumption and it's incorrect. So yeah, I hope that helped vaguely. It's an answer. It's probably not a perfect answer, but that's, I think, what's going on. Okay, bye bye.